All right, let's see how you made out with number 2. In number 2, we're asked to find any vertical asymptotes and horizontal asymptotes. So the function is f of x equals 7 divided by x minus 4. To get the vertical asymptote, set the denominator equal to 0, and we see that x equals 4 is your vertical asymptote. For the horizontal asymptote, we notice that the degree of the denominator, m, is greater than the degree of the numerator, which is n, which is 0, right? M is 1, n is 0. So in that case, we have the x-axis as our horizontal asymptote. That is y equals 0. Okay. So let's put all the pieces together and draw a pretty complicated looking rational function. For an example, I chose problem number 16 on page 488 because it's an even numbered problem and I wouldn't want you to have to try to do it at home alone without the answer in the book. For part A, figure out the horizontal asymptote. Well, m is the degree of the denominator, right? And it's 1. N is the degree of the numerator, and it's 1. So m equals n, which means that the horizontal asymptote is the ratio of the lead coefficients. So it's 5 over 1. Right, so the line y equals 5 is going to be your horizontal asymptote. And you can see that if you start choosing some large x values, 10, 100, 1,000, that minus 3 hardly matters anymore as x gets bigger. You're going to have 5 times x over x, so you see how it's going to go to 5. Vertical asymptote. Set the denominator equal to 3, equal to 0. I think it's getting late in the day and I'm getting tired. So the vertical asymptote is positive 3. Now I've already drawn my vertical asymptote and my horizontal asymptote in on my graph here, and I've already calculated a bunch of points. I have 0, 0, 1, negative 5 halves. Put some gradation markers in here. Negative 5 halves, that's negative 2.5. 2, negative 10, so it's going to be way down here. 3 can't go in there, right? It's not in the domain of the original function. 4 gives me a positive 20, so I'm way up here. 5 gives me 12.5, so I'd be maybe around here. 6 gives me 10. 7, okay, so 3, 4, 5, 6, 7. 7 gives me 35 over 4, which is 8.75. So it's about there. I guess it's a little higher up. And negative 1 gives me 5/4. So I'm there. Negative 2 gives me 2. So I'm there. All right, if I connect all these dots, I think I can convince you that the graph looks like this. Up here, I think I can convince you that the curve is asymptotic with this x equals 3 line. Let's move that point over so it lands where we want it to. And this, yeah, I guess we go down more, steeper. Eventually is going to be asymptotic to x equals 5 as x goes off to the right here. That is to say, as x goes off to positive infinity. Alright, so that's how we use asymptotes to graph a rational function. Basically, you just look for your asymptotes via these two methods, and then after that, you just have to plot points. Of course, you do have your experience to call upon. You know that you're going to have this kind of curvy shape, probably in a couple different pieces, so you can do that. Now, you work one out. On page 487, do number 18. Page 487, number 18. Find the asymptotes for that function and go ahead and graph it. Were you able to do number 18? Here's what your work should look like. The function is f of x equals 2x squared plus 1 over 2 minus x. I see that n, the degree of the numerator, is equal to 2. M, the degree of the denominator, is equal to 1. So for my horizontal asymptote, I see that n is greater than m, which tells me there is no horizontal asymptote. You can sort of mentally double check that if you think, okay, what happens as x gets very large? 10, 100, 1,000. Right? We're getting 10 squared, then 100 squared, then 1,000 squared. The numerator gets very, very large. The denominator, not so much. Right? So the numerator kind of overwhelms the denominator. So f of x just keeps getting bigger and bigger and bigger, and it's never going to get leveled off at some kind of horizontal asymptote. Part B, your vertical asymptote. Set the denominator to equal 0, and we figure out that x equals 2. So I've drawn that vertical asymptote, x equals 2, on my graph. And I've also calculated a bunch of ordered pairs for the function. And I've plotted these points. And you can see the pattern over here. The curve is going up asymptotically, approaching the vertical asymptote x equals 2. Here, curve is going up, but it's not approaching anything asymptotically. Down here, hardly had any space to get these numbers. These big negative numbers plotted down there. But you can see, and of course the graph in the book is a lot better, you have a curve going on down here. And this side of the curve is asymptotic to x equals 2. Now, there is no horizontal asymptote there. But in fact, I can draw you a line in my green marker here, and I'll fix up my original graph so that it all works out happily. The next thing we're going to learn is that there actually is an asymptote here. It's just not a horizontal asymptote. This slanted line here that I drew in the green dashes, the curve approaches it asymptotically, gets forever closer and closer without ever touching it. Same thing down here. This branch of the curve down here asymptotically approaches that. Let's see what's going on here. So this topic is entitled Slant Asymptotes. And the rest of the section is called And Missing Points. But that's actually a different idea. Slant asymptotes. Look at example 4. F of x equals x squared plus 4 over x minus 2. I see that n is equal to 2, m is equal to 1, and as we just did in the example we just finished, we say, oh, there's no horizontal asymptote because n's bigger than m. But it turns out that if n equals m plus 1, then there is a slant asymptote. So if the degree of the numerator is 1 larger than the degree of the denominator, there is a slant asymptote. That's the case here. So we're going to see a slant asymptote when we graph this function. To find it, divide the numerator by the denominator. The denominator is x minus 2, so to divide it using synthetic division, we divide by the root of x minus 2, which is positive 2. We're dividing into 1, that's 1 times x squared, then it's 0 times x, and then your constant 4. So that is the synthetic division problem that we want to do. Bring down the 1, 1 times 2 gives me 2, add them up, 2, 4, I have a remainder of 8. Well, that tells you that x minus 2 is not a factor of x squared plus 4. But it also tells you this, that x squared plus 4 equals this factor times this factor. Remember, that's the x column, this is the constant column. So this factor here is x plus 2. And there is a remainder of 8. So the numerator can be rewritten in that way. And it is this quotient here, this quotient that we arrived at in the synthetic division, which is our slant asymptote. In other words, y equals x plus 2 is the slant asymptote. Vertical asymptote, that's easy. It's when x minus 2 equals 0, it's x equals 2. And of course we always have to check that this number here does not make the top equal to 0. You only have a vertical asymptote when the denominator goes to 0 while the top does not. And we see that x equals 2 will not make that 0. In fact, no real number will make that 0. So, with all these pieces of information, we can draw a nice picture. I'll count in fours there because the numbers are getting kind of big. Yeah, I'll count in twos here, that fits better. 2, 4, 6, 8. -2, -4, -6, -8. Vertical asymptote, x equals 2. Slant asymptote, y equals x plus 2. This is 4, so here's 2. There's my y-intercept. The slope is 45 degrees because, I'm sorry, it's actually going to look flatter because I have a different scale here, right? This is 2, 4, 2, 4, 6, 8. This is 4, 8, 12, 16. So it's doubled. The scale is doubled. So my vertical asymptote is the line y equals x plus 2, and it would look approximately at that slant. Then I start plotting points. This one's here, this one's here, this one's here. This one is my y-intercept. This one. A couple more over here. And you can see what's going on. There's the asymptotic effect there. There it is going to the slant asymptote. And here, sloppy drawing, but you get the idea. We have that asymptotic effect over there. Slant asymptote. So, let's see if you can do one. On page 488, number 22. 22 on page 488.